last lesson, we looked at what happened if we took parallel plates and charged them. We would create an electric field between the plates because of the voltage difference between the plates. And we know that wherever there's an electric field, if we put a charge there, then the electric field will exert a force on the charge. So in this lesson, we're going to look specifically at forces on charges between parallel plates. So remember from the last lesson, we had this system where we charged our parallel plate so that usually one plate is positive and the other plate is neutral, although we refer to it as a negative plate because it's got a lower charge or lower voltage than the positive plate. And in between there, we create an electric field measured in newtons per coulomb or volts per meter that is uniform, meaning the same everywhere inside the plate. And the direction of the electric field is always away from the positive plate towards the negative plate. Away from the positive plate towards the negative plate. And it is the same value no matter where between the plates that we are. And the strength of that electric field is determined by the voltage difference across the plates and the plate separation. How far one plate is from the other plate, not the distance from one plate that we happen to be, but the distance that the plates are from each other. So, using that idea, explain why an atom will be ionized, which means the electron will be separated from the atom if it is placed in a sufficiently large electric field. So we take our neutral atom that has a positive nucleus and a negative electron, and we put it in an electric field. Why will it become ionized? In other words, why will this electron get separated from its atom? Well, the answer to that is that we know that this electric field will exert a force on the electron. So that force will pull the electron away from the atom. So the electric field exerts a force on the electron, which pulls the electron away from the atom. And in the case of our diagram here, if we have a large electric field going to the right, our electron will feel a force to the left. This would be the electric force on the electron that rips it off its atom. So there you go. If we're talking about air, which is a mixture of nitrogen and oxygen and other trace gases, it takes about 3 million volts per meter to produce ionization. In other words, to rip the extra electrons off the nitrogen and the oxygen. This may seem like a lot, but in actual fact, ionization of the air occurs frequently, and here are some examples. The crackle we hear when we pull apart clothes that come out of the dryer, that's ionization. The shock we get when we walk across a carpet on a cold winter day and then reach for a doorknob, that's ionization. And lightning is also another example of ionization. So each of these effects is accompanied by light. And this light occurs because the ionized electron does not remain free. It will actually quickly fall into an orbit around a neighboring atom before maybe getting ripped away again. And when the electron does this, some of its energy is converted into light energy. So that is what we call static electricity. So pause this video for a minute and take a quick foray into another world. Go ahead and watch Daft Punk's Derez performed with the Tesla coil to see some examples of ionization. Pause your video, click on the link, come back in a minute. Pretty cool, huh? Bet you didn't know ionization was so common. Let's look at a couple more examples. The bottom of a cloud is charged to 2.5 times 10 to the 8 volts by cosmic rays that pass through the atmosphere. So the bottom of the cloud has 2.5 times 10 to the 8 volts. How close does this cloud need to be to the ground for a lightning bolt to occur? And here's a little bit of extra information. It breaks down at about 3 million volts per meter. In other words, this is the electric field that we need. Remember, volts per meter measures electric field in order to get a lightning strike. Now, normally the ground is actually neutral. It would be at 0 volts. So we need to figure out what what separation distance between the clouds and the ground would produce this 3 million volts per meter. So I have, this is still from last class, my electric field is equal to my change in voltage over the distance of separation between my two plates, in this case the cloud and the ground. And I'm trying to find D, so I'm going to solve for D by moving it up to the other side and then dividing the E out. So I've got D equals delta V over E. And then I just plug in my information. So my top V is 2.5 times 10 to the 8 volts minus the 0 from the ground divided by 3 million is times 10 to the 6. And this gives me a separation distance of 83.3 meters. So not actually super big in order for us to get a lightning strike if I've only got 2.5 times 10 to the 8 volts. So if lightning striking from higher up, you know that the voltage difference must be greater in order to get our 3 million volts per meter that we need in order to ionize the air. Another video break, how to survive a lightning strike. Very important to know. Go ahead and pause your video, take a look, and then come back and continue your notes. Alright, hopefully that will one day help you to survive if you ever end up in a storm and you need to get out of the lightning. Recall that if a field is known, in other words, we know how big the electric field is, we can find the electric force on a particle as follows. I've got F equals Q times E, where F is the force on a test charge Q, Q is the test charge in coulombs, and the E is the electric field at the location of the charge. So if I'm thinking specifically in the context of parallel plates, then I know in that case that E is delta V over D. So I can sub that into this equation to get F, which is Q times E, is going to be Q delta V over D. So that's just kind of handy to have around. You hopefully can figure that out for yourself if you need it in the future, but for now, we're going to use that in our next example. Find the acceleration of an electron placed between metal plates that are separated by 2.50 centimeters and charged to 2.75 volts. So I've got 2.75 volts voltage difference. So this is going to be my delta V, because it's 275 divided minus 0. The 2.5 centimeters, that's going to be my D, my difference. And what is it actually asking me for in this question? It's asking me for the acceleration. Well, wait, we haven't seen anything to do with acceleration yet. So how is acceleration at all related to this question? Well, if you remember, all the way back probably from 10th grade, we had this equation that said F net equals mass times acceleration. So if I can figure out my force on the electron, then I can figure out what the acceleration on the electron would be, because acceleration is going to be F net over over m. So my net force in this case is going to be my electric force, and that's because of the charge difference between the two plates. So I'm going to use that equation that I found on the previous page that says F net is going to be Q delta V over D, and all that's divided by m. Or I can simplify that to be Q delta V over D times m, since both of them are dividing. Then it's just up to here. I need to plug in the information that I know. So Q is the Q of the electron, and we're talking forces. Force is a vector, so we aren't going to put the negative in. We're just going to put 1.6 times 10 to the minus 19. My delta V is my 275 volts minus the 0 volts. My distance that I'm separated is 2.5 centimeters, which is 0.025 meters. And last but not least, the mass of my electron, you can look up on your formula sheet, is 9.11 times 10 to the minus 31 kilograms. So I want to plug all that into my calculator and see what it gives me. And my calculator tells me I've got an acceleration of 1.93 times 10 to the 15 meters per second squared. Huge acceleration. Because my electron is so tiny, so little weight. All right, let's keep going. In a very famous experiment to measure the charge on the electron, Millikan used parallel metal plates to hold in place a charged oil drop. The oil drop remained in place because the electric force, due to the metal plates, balanced exactly the gravitational force. So here we go with example number 5. The charged oil drop below is at rest due to balanced gravitational and electrical forces. The two are equal. In other words, we're going to start it with something like Fg equals Fe. Electrical force equals the gravitational force. What is the sign of the charge on the oil drop? Well, if I think about what direction each of these forces have to go, in order to balance each other, they must be in opposite directions. So I know that the force of gravity must be downward. It's always downward. And in order to balance that, that tells me my electric force must be upward. And in order for my electric force to be upward, that means whatever charge I've got is being attracted to my positive plate, repelled by my negative plate, attracted to my positive plate. And what kind of a charge is attracted to a positive plate? Well, it must be opposites attract. The sign of the charge must be negative. Then it says, write a balanced force equation in terms of the variables on the diagram and the gravitational field G. In other words, we don't have any numbers to plug in yet. We only have V, M, Q, and D. But we can start figuring out what our formula would be, and then actually in the next example, we're going to actually plug in some numbers. So Fg, hopefully you remember from grade 10, is equal to mg. And Fe, which we just saw above, was Q delta V over D. So this would be my balanced force equation in terms of M, that's given in my diagram, G, that's the gravitational field strength, Q, given in my diagram, delta V, well hang on, I don't have delta V in my diagram, I have V and 0. So I'm going to actually take this one step further to say, well, delta V is V minus 0. It's just going to be V, so let me rewrite that, mg equals QV over D. And D is in my diagram. And that would be my equation in terms of the variables in my diagram. So I haven't been told what I'm looking for. I haven't been told what any of the numbers are, but that would be my balanced force equation. Looking at example number 6 then, a particle of mass 2.3 times 10 to the minus 14 kilograms. So now they're starting to give us information. So here's my mass. And charge negative 3e. Remember, E is the elementary charge. It's like 3 electrons. Well, in this case, it is 3 electrons because it's negative. So this is going to be my Q, or tell me my Q, is held suspended between 2 parallel plates. What is the voltage, that's what I'm looking for, find V, on the upper plate in order to keep the charge in equilibrium? So I look back at this equation and I go, okay, in this equation, what I really want to find is I need to solve for V. So I'm going to move D up to the other side. That gives me mgd equals Q times V, and then divide by Q to get V by itself. So I've got V equals mgd over Q, and hopefully I've got enough information now to be able to fill in what I know. So M, they told me 2.3 times 10 to the minus 14. G is my 9.8 meters per second squared from gravity, and my D is my separation distance, which on the diagram tells me 1.5 centimeters, so that's 0.015 meters, all divided by negative 3e. So in other words, I'm not going to put the negative in, because if I've got a negative charge here, if this is negative 3e, this voltage must be positive in order to be able to attract this charge. If it's going to be a negative voltage, it's going to actually repel this charge and the charge is going to fall. So I'm going to put in just 3 times 1.6 times 10 to the minus 19 and see what that gives me. And my calculator reveals that I need a voltage of 7,040, out onto the 3 sig figs, 7,040 volts in order to keep this negative charge suspended due to gravity. So that's it for forces and parallel plates. In the next lesson, we're going to look at energy in parallel plates, and then we'll wrap up the unit. Good luck with the homework.